And our last speaker of the day is Dave Bhella from Glasgow, who's going to tell us about all things JEOL.
Right, can everyone hear me? Yes. Silence. Okay, good. All right then, let's get started. So I should start by thanking John and Becky for the kind invitation to come and talk today about our experience as early adopters of the JEOL Cryo-EM 300. So in SCMI, we took the decision to buy JEOL's automated 300 kilovolt Cryo-EM, and we also took the decision to buy Direct Electron's D64 camera. So this was quite a big shift for us away from the established instruments that people are using, and so I wanted to tell you a little bit about that. And I also should apologize that I'm not going to show you a slide stack full of benchmarking data, and because we've still had relatively small amount of time with the microscope, although installation started last April, but it's as you can imagine, it's a new microscope, relatively new camera. There's a lot of work to be done to make it all start to sing. But for my talk, I'm going to start by giving you an introduction to Cryo-EM in Scotland, how the SCMI came to be, about the organisation, about the consortium, our procurement decision-making process, before I then go into a technical overview of the instrumentation we bought, some of the bumps in the road, what works, what doesn't work yet, and then I'll finish up by showing you some of our preliminary data or recent results from the microscope. So in Scotland, there's been a healthy interest in Cryo-EM for quite a long time. I work in the MRC Centre for Virus Research, which is based in the University of Glasgow, and there's been a link between MRC virology in Glasgow and Cryo-EM since possibly the dawn of Cryo-EM time, going back to this collaboration between my colleague Fraser Rickson and Hua Chu, which led to this early paper describing the first structure of the Herpes Simplex virus capsid in 1989. On the back of this very strong and productive collaboration between Fraser and Hua, the director of the institute took a decision to try to work towards establishing an in-house Cryo-EM capability in the MRC virology in the University of Glasgow, and that was started under the leadership of Sarah Butcher in 1996. She stayed in Glasgow for 2 years before moving to Helsinki, and I then came in 1998 to take over where she'd left off. And at that time, we were working with 120 kilovolt Lab 6 TEM, a little film scanner, and I spent, my first experience of spending public money was spending £65,000 on an SGI octane that had some vanishingly small amount of memory. So we published our first 3D structures in 2004, and that supported our purchase of our first FEG instrument, JEOL 2200, which we installed in 2007. And that was our frontline instrument for the next decade. So we were joined by Laura Spagnuolo in 2015, who came to the Institute of Molecular Cell and Systems Biology in the university, and we have now a very large group of PIs, crystallographers, structural biologists, and molecular biologists who are very keen to use Cryo-EM. Scotland, before SCMI, Scotland did have a national Cryo-EM centre, which was established under the leadership of Bettina Bircher in Edinburgh. That was equipped with a Techni F20, and Bettina moved away from Edinburgh a couple of years ago, and since then this microscope had been managed by Fabio, and Edinburgh was recently joined by Marcus Wilson from the CRIC, who's now leading Cryo-EM in Edinburgh. And there's also a Cryo-EM group in Dundee under the leadership of Tom Owen Hughes, and they started really with a second-hand, very old JEOL 2010F in 2014, I think. So a lot of people interested in Cryo-EM, a lot of people trying to develop their Cryo-EM expertise. And back in 2015, before Laura came to join us, when she was still in Edinburgh, she convened a meeting of all structural biologists, the Scottish structural biology community, came together in Edinburgh to discuss how are we going to work towards establishing the sort of capability we would really like to see. And this was a really, really productive meeting. It built a network of investigators that was really the basis of establishing the SCMI consortium. We started working very closely together. We ran some training workshops in Glasgow, teaching people how to plunge grids and working with them on our 2200. And this was so that was a really pivotal meeting that Laura organised. It was very helpful. So it meant that when Wellcome announced their call for investment in Cryo-EM, we had a consortium building. We had the grounding of a consortium to allow us to come together and write a proposal for funding for a high-end automated 300 kV microscope for Scottish structural biologists. So we put together a bid to this call that was a consortium between 4 universities here, Glasgow, Edinburgh, Dundee, and St Andrews, which seem to have disappeared off my bulleted list here. So sorry, St Andrews. Oh no, okay, that's because they don't have a feeder microscope. Right, so it was Glasgow, St Andrews, Dundee, and Edinburgh. And we, with Newcastle and Aberdeen cheering from the sidelines, that we put together this proposal to Wellcome with a really strong consortium where we put together more than just we want to buy a automated 300 kV microscope. We put together this network of feeder instruments that would serve, that would allow project development in each of these institutions and allow those projects to be well developed by the time they're presented at the high-end microscope, which is based in the Garscube campus of the University of Glasgow, which is where my institute is based. So we put this application into Wellcome. Wellcome declined to fund it, along with a few other very, very strong applications, and those applications were passed to MRC. Obviously, we're part of an MRC institute, so we have a very strong relationship with MRC already, and that sort of then led to about 7 months of sort of nervous waiting and chewing of fingernails while we wanted to see whether MRC were able to get the funding for our centre from government. And then, happy days, in July 2017, we got this lovely letter saying that we were going to be awarded £4 million from MRC to get SCMI set up. And this is when reality really hit home. And it's like, okay, now I'm leading a consortium. We're responsible for spending a colossal amount of money. We have to buy a Krios. And we have to and having had a very, very long relationship with JEOL over the years, JEOL had been talking to us and saying, well, what do you think? Do you think you might be interested in going with us? And I think I estimated the likelihood about 2% at that time. But we were entered into a very robust procurement process, tendering process, and in that time we went to Japan to see a demo of the prototype instrument in Keiichi Namba's lab in Osaka, and also some instruments in the factory. And these were phenomenal demonstrations, and we were really bowled over by the amazing engineering and the very strong proposition that JEOL were putting forward. So I've seen a lot of EM demonstrations in the course of my career, and when you're doing a cryo-EM demonstration of a microscope on somebody else's microscope in a research lab, there's a lot that can go wrong, and most of the demos I've seen in the course of my career have been absolute train wrecks. This one was flawless, and some of the things we were really impressed by I'm going to tell you now. And between us as our procurement committee, that's myself and James Streetley and Laura Spagnuolo, we sort of came round to this idea that the JEOL cryo arm was a really, really strong prospect. And thankfully, when we came back to Scotland and discussed that with our colleagues in the consortium, they were very, very supportive of it. And I think possibly one consideration in their support was the fact that we have access to EBIC and we have a Scottish bag, which meant by going down this route, which means that we're probably going to take longer to delivering a service, it wasn't like a disaster that meant that there was going to be no microscopy happening. So everyone was very supportive, and everyone was up for this. And it was so this is what we did. We bought the JEOL cryo arm, which I'm sure many of you are already aware what the instrument is. It is a fully automated 300 kV microscope that has a 12-slot, 12 specimen autoloader, full automation for single particle and tomography. It has an in-column omega-style energy filter, phase plates, and of course the thing that is pretty interesting is that it has the new JEOL cold field emission gun. For us, it was also interesting that it came with STEM as standard. So things we really liked about this were these. We really liked the design of the autoloader, and we really liked these two things here, which became a really sort of interesting prospect for us. So once JEOL had become preferred bidder for us, we then entered into discussions with them, and they offered us for our budget this microscope plus a 200 kV side entry feeder microscope, which also has a cold FEG, ARM lenses, and STEM for the budget that we had. And that was also a very attractive proposition because that meant that our existing feeder microscope could be passed to Dundee, which increased their capabilities. So great. So for £4 million, we got 2 microscopes, which was very competitive. So I will tell you a little bit more about this sort of technology. So how a grid's loaded into this autoloader system. So grids are retained in these cartridges, which are sort of metal bars. You can see the grid sort of sits in here, and it's held in place by a clip ring. It's loaded into this cartridge in a very well-designed ergonomics loading station. So we have the tools here, the cartridge sits here, and this is where we do the clipping. And then once the grid is clipped into this cartridge, it gets moved into this magazine here. And then that gets slipped into this cup here, which is then lifted out into the transfer cup, which can then be loaded into the microscope. So this is actually our cryo arm sitting in its room. So it has a great big white box instead of a great big black grey box. But, and the only thing that you can see inside the microscope is if you open this panel here, then you start to see this is where the cup is inserted into the microscope. So you can't see I can't show you pictures inside the box of the column and the components. And this has the effect of making this look like the largest espresso machine on the planet. So we have a touch screen here that just initiates that automation of loading of the magazines into the autoloader. So grids are loaded in sets of 4 in these cartridges, and they are moved. So this is sort of the computer display. This shows the sort of schematic. So we have the cartridge, the magazine here, and then we have a storage area here which holds the 12 grids. So all the grids are moved in. You can associate names with them and data with them, and they're all tracked as they're moved to and from the stage. So what this means is we can load 4 grids at a time, we can move them into storage, we can image them, we can take 2 out, we can put another 4 in, we can take 3 out, you can leave a grid in there for 2-3 weeks if you want to, or months if you need to. And that also means that this storage area is not vented regularly. It's only really vented when we warm up the autoloader. So this all stays under vacuum, which keeps it very clean, which is very nice. So that's one, I think, thing that really impressed us about this whole design. I think it's very, very well thought through. We don't put 12 grids and take 12 grids out. We can put any permutations in and leave grids in if we want to, or we could leave a standard in there for just evaluating, checking the column. So automation with this microscope comes with 2 software packages supported by JEOL, their own single particle automated data collections program, JADAS, which I really like. It's very, very nicely designed, easy to use, and the sort of the idea, what the JEOL are trying to achieve, is something that involves minimal user input. Effectively, you just montage your grids, select your grid squares, and off you go. That is not fully realized, but it's really getting there. So I think it's very nice software to use. I really quite like it. And for us, this is working nicely for single particle data collection at the moment. It handles the flashing of the cold FEG automatically, so you don't have to think about that. It can handle the phase plates, advancing of the phase plates automatically, filling of the liquid nitrogen dewars. It's all, as you would expect, fully automated. So for tomography, JEOL supply supported installation of serial EM, which of course can also be used for single particle data collection, and I think we're very interested to explore using serial EM for single particle data collection for its great flexibility, as we've heard from many speakers in the course of this discussion today. So we have the cold FEG. I don't want to say, I'm not here to sell the cold FEG as a great concept. I think it remains to be seen whether the reality matches the promise, but the cold FEG does have a narrower energy spread, and certainly in material science this has proved to be really, really instrumental in improving high resolution that allows you to get sort of sub-angstrom resolution in material science, and for us I think it potentially could be useful, so you have better signal at higher resolution. And I say correlation doesn't equal causation, but many of you may have seen this on Twitter, which is a very high-resolution apoferritin structure collected from a comparatively small amount of data in the Spring 8 microscope in Riken. So that's very nice to see. It was very exciting for us to see this because it sort of kind of validated our idea that this was not a crazy thing to do. So that's the microscope. So why did we buy the direct electron DE64? So the DE64 was presented to us as one option, and the DQE curves for the DE64 look pretty nice in the two counted modes. So this is unbind and bind 2 counting DQE, and this is the sort of linear linear DQE, which is kind of what you'd expect. So I was very interested in this for a number of reasons. Firstly, for tomography, having a large field of view is going to give you a lot more data for your tomogram. And we do work on a lot of large objects. And sometimes this can be deeply, deeply frustrating. So this is an image from a Falcon 3 taken at 1.78 angstrom per pixel. And these are herpes virions, and you can see you've got sort of relatively poorly concentrated virus prep, and of 4 particles in this field of view, only 2 are usable. So with a bigger detector, we can get more objects onto the detector and at higher resolution. So, of course, I'm not buying this for me, I'm buying this for everyone, and it was a group decision. So we wanted to be sure that this would also deliver for everyone else. And I think those counting statistics, the counting data, the DQE for counting really sort of convinced us that this would be a viable camera for single particle data collection of small objects as well. So I think it's a very flexible camera. But you can maybe see from this image that things are not all completely perfect. There's some stripes in this. There were some problems referencing, and we have experienced several problems getting good referencing on this camera in the course of the last year. So that brings me to my slide, which is my sort of moans slide, the bumps in the road, the difficulties we've had along the way. And I'm going to sort of break this down according to difficulties we've had with the camera and difficulties we've had with the column. Before I start, it's important to say that the vast majority of these issues are resolved. So with the D64, initially we had some problems with the mechanical shutter repeatedly failing, which was deeply frustrating because we're just trying to move forward, and then all of a sudden the camera's got a big sort of shutter over half of the sensor. That took direct electron a little while, 3 goes to fix, which involved Mike Spillman coming from the States to do that. So that was challenging. We've also had problems with server instability and slowness, switching mode, things like this, with the D64 software, and problems with reliable referencing. For a long time, bind counting was not reliable or functional. But these are all now resolved. With the cryo-arm, we've had some issues as well. I've got a bit thing here, like autoloader issues. Actually, we've had hardly any autoloader issues, and most of these autoloader issues are actually, in reality, inexperienced user issues. So we had some issues where the magazine would sort of freeze onto the robotic arm that sort of moves things in and out, and we had to sort of work out a way of fixing that. But apart from that, the autoloader has proven to be very, very reliable and very easy to use. We've had a couple of phase plate heater failures, and that's something that's still requiring attention from JEOL. And I think the thing that's probably taken the longest time in the whole past year of getting us from where we started to where we are now was getting the automation to really work seamlessly and reliably. And I think probably this is really caused by lack of experience, lack of expertise, both on our part and on JEOL UK's part. And I don't think it's really terribly surprising when you're dealing with an entirely new microscope. So we had some issues with the engineer column alignment not being quite suited to automation. But again, largely resolved. Finally, we've also had some issues with the energy filter instability, which turned out to be tracked down to a problem with our chiller rather than the microscope. So we're waiting for that to be resolved by the chiller provider. So all of these issues, which I've spent a little while complaining about, are actually now largely resolved. So we are now moving towards a position where we can really do automated data collection and consider having external users come in and collect data on the microscope. So to show you some of our first data. I'm going to start with tomography. This is actually a tomogram. I'm going to show you a tomogram that was actually collected fairly early on in the whole process. So again, we have this sort of referencing issue, which has now been resolved. The stage tilts very nicely, and full automation of tomography now is implemented using serial EM with bidirectional data collection. We have not yet implemented dose-symmetric data collection, but I really feel that's sort of a matter of us just devoting the time to it. There's nothing really obviously wrong that should stop that. One of our first single particle projects was that herpes virus capsid that I showed you. We collected some data that looked like this, which was lovely because we've got the big detector and we've got all these particles imaged at high resolution, but you still can't legislate for fate. We still got a lot of micrographs that look like this, which was kind of frustrating. So in that data collection session, we got about 4,000 particles, which gave us a resolution of about 7 angstroms, which is more or less comparable to what we've achieved with the Falcon 3 on a Krios. So no surprises there. So the last structure I'm going to show you is one that we have done in the last 3 weeks. It's a structure of an enzyme complex called Lumazine Synthase. Lumazine Synthase is something that a group in the CVR is interested in using as an antigen display platform. It's a nanocage, it's an icosahedral, small enzyme complex. And you can see from the image why we decided it might be a good idea to try and solve the structure of it. They can produce 8 milligram per mil preps of this protein, which are beautiful. So Mary Clark made some cryogrids of this material, and we popped it into the microscope. So this is the best micrograph that was captured. And I think you can see that even in this best micrograph, although we've got wall-to-wall particles, the ice is a bit thick and there's particles stacked up here. And for a lot of the data, the ice was thicker than we would have liked. These are the sort of imaging conditions. So data collection is kind of K2-like. We're doing 10-second exposures and writing out 40 frames in a movie. And this is bin 2 counting. So this is 4,000 by 4,000 image. So kind of K2-like in its imaging. So this is the power spectrum of that image, and as I say, the resolution estimate by GCTF was 1.78 angstrom. And if we zoom in on there, we can see sort of ton rings coming out through the water ring, which is nice. These are some class averages, which were beautiful. And in this so in that data set, there were about 150,000 particles auto-picked. Most of them were in very, very thick ice. After 2D classification, that was distilled down to 60,000 particles, and after 3D classification, that was distilled down to 22,000 particles. That gave us a structure at 2.4 angstroms resolution. So this is just the surface representation of that. So I was quite happy with that as a resolution for our first sort of new counted data set, and that's not apoferritin. So this is just an image from Coote. So we didn't have to build a model into this because the structure has already been solved by X-ray crystallography quite a long time ago. So just docking that model in, you can see the density matches the X-ray structure very, very well. And one thing I really liked in this, which was kind of a novelty to me, but may not be to many of you, was that in this density map, we could see a lot of water molecules that were annotated in the PDB file from the crystallography data. So you can see a lot. So that was nice to see that sort of correspondence between our Cryo-EM map and the X-ray structure. So this is the B factor plot, the automated B factor plot that were calculated using Shaw's script, which tells us that we would need about 180,000 particles to get beyond 2 angstroms. But I kind of feel that if we can get the ice thickness a bit better, we might do a bit better in that respect. Okay, so just to sum up. So the cryo-arm was selected on the grounds of several novel technologies that we're very interested in, some very good engineering and innovative design. We selected the DE64 for the large detector and the good DQE. The cryo-arm installation started in April 2018, and for most of that time, we've been engaged in software setup and hardware performance troubleshooting. and developing workflows. And we are still working on workflow development. But I feel now that we have a minimal set of workflows that we can go. We can do linear data collection around 1 angstrom per pixel. We can do bin 2 counting at sort of higher resolution. We should deliver high resolution single particle data. We can do bidirectional tilt series automated tomography. So on those grounds, I kind of feel we're ready to move into a service delivery sort of phase. So it just remains for me to sort of acknowledge the many funders who've contributed to this. Of course, MRC sort of came good for us with a very large award. We've also had funding from the Scottish Funding Council and the Scottish Universities Life Science Alliance. And these are the partner institutions that have all individually ponied up several £100,000 to get the whole project off the ground. And key people who need to be acknowledged. So the co-investigators on the grant were Jim, Tom, Atlanta, Laura, and Danny Huang from the Beatson Institute, and myself. Uli was not a co-investigator, but is now, in Jim's absence, has moved on to the management group. Of course, great thanks to the External Scientific Advisory Group that have sort of given us a lot of really, really valuable input in the course of this whole process. And finally, acknowledging James and Mari, who are the people who are going to run the centre and hopefully deliver great data to all our users. Arvind, Vanessa, and Sarah provided the Lumazine Synthase. Fraser and Sweta, who's here, Sweta Vijayakrishnan, who's here, is not on the acknowledgement slide because I thought the flu virus came from Michaela, but it actually came from Sweta. So apologies for that. And of course, JEOL and Direct Electron. And that's me. Thank you very much. And just for fun, I'm going to show you. This is the microscope running now. We set the microscope running on Friday, and it's still going. You'll see it's not going. It's not a bat out of hell. It's in the time that it's been running, it's collected near just approaching 3,000 micrographs. But it is still alive. It's still working. Automation is running. Thank you.
Right, thanks, Dave. I've got a question. Don't you owe me a session on that microscope?
Yes, I do. Do you want it now, or do you want to wait till it's...
Just might come and have a play.
Yes.
Serious questions for Dave? John.
So you have a unique experience of having used the Titan Krios and the JEOL arm. What would you take from the Krios and put on the arm, and what would you take from the arm and put on the Krios?
That's an interesting question. I really like the Falcon 3, and that wasn't an option for us. I think that would have been an option. Of course, that's yeah. I mean, the Krios software is much more mature. But I think we're going to get there with the JEOL software. I think the autoloader on the cryo arm is just amazing. I think it's brilliant. I think it's so well designed. So yeah, I would. I think that's something you might. They're clipped into those sort of they're clipped into those cartridges which are about an inch long, and then those are loaded into a magazine.
Are those consumables?
No, they're reusable. The clip rings are the consumables. Just a little sort of C-clip that holds the grid in place is the consumable.
And can you get a cold grid out to the microscope cold?
Not yet. Yeah, so that's, of course, the big limitation. I gather the JEOL are working on that, but at the moment, once the grid is in, it's in. But it can stay in for a month if you want to collect on it again, or more.
Morgan,
Hey, David. Really exciting. Can you say anything about the faceplate? Any experience? Does it work?
We have not used them in anger. Superficially, I can say yes, they work. I've seen faceplate images from the microscope, and I've seen the faceplate be advanced and conditioned by automated software. But yeah, we've kind of we don't want to add sort of too many layers of complexity to the thing at this early stage.
John, do you want to?
So where it's slower at the moment is it's not doing multi-shot. So if we are doing unbinned linear data collection, where you have that big 8K image, we're running at about 60 movies an hour, which isn't lightning fast, but it's just a single shot per hole. And with the binned counting, it can be a bit slower because we're doing longer exposures. But I think once multi-shot is implemented, which of course, I mean, in principle it is, right? We haven't got that far. I mean, it is possible in serial EM. So, and it is actually written into JADAS, but it's just not properly implemented in a way that's particularly useful at the moment. So, once multi-shot is working, then it will be faster. It's not going to be. I mean, the frame rate of the camera is slower, so it's not going to be as fast as the K3. But I think once multi-shot is in, it will be similar to a K2 in its throughput.
I noticed that your is it Lumazine Synthase?
Synthase, yeah.
Synthase. That was binned counting.
Yes.
Do you have an unbinned counting data set to compare it to?
Not yet. Not a good one. So yeah, we need to do more work on ensuring the stage stability to do unbinned. Yeah. So I think there's a lot of that's in the software, you know, just the sort of backlash settings and things like that to get the stage stability where it needs to be for unbinned counting.
Okay, I think in the interest of time and having a working group 1 meeting, we better finish. So can we thank both Dave and Felix?